Let's start by going back to example 5.1 where we demonstrated Fermat's factorization method to factorize this number 119143. So the method simply was this. First you have to find an integer whose square exceeds your given integer. Now if you are extremely lucky, and this will rarely happen, you will come across a square which is equal to the given integer. If that happens, then of course you already have a factorization, and you will then go looking for ways of factorizing that number itself whose square is n. But that rarely happens. So in this example, that integer is 346, and then we go like this. So first we subtract n from 346 square and see whether the result is itself a square, and we are looking for such squares. That's not the case here. We then increase this number by 1 and again go like that. So this way, if we go and we eventually reach a square, then we get a factorization of the given number like this: a plus b times a minus b. However, if we do not encounter any square and eventually reach the stage where, say, in place of this number you have n plus 1 over 2 whole square minus n, then on that other side you do have a square which is the square of n minus 1 over 2. But if that's the case and you did not encounter any square before getting to that stage, that means n is a prime, because the only factorization of n possible then is the trivial one, where one of the factors is n and the other one is 1. So in that way we calculated and found that we have this first occurrence of a square 69, and that's how we got the factorization of our number n. Now you may remember that while discussing this example, I made the remark that it may take some effort to figure out whether these numbers are themselves square or not. Okay, that itself may take some effort. But how do we do that? Is there any way of reducing our labor? Say, is there any way to rule out some numbers quickly by looking at them and figuring out, oh, this cannot be a square, this cannot possibly be a square. So that's what we are going to discuss first today. To do that, what we do means, what the author has done is he has found the last digits of any square by going through this type of congruences. X square congruent to k modulo 10. We already know from our congruence theory that when we find this k here, which is a single digit k, then that becomes the last digit of the number x square. And also, because the modulus is 10, there are only finitely many possibilities. So these are the possibilities. These are the possible last digits of any possible square, any square of any integer. And we have already actually proved this in this exercise. What does it mean? It means that if a number is a perfect square, then its last digit has to belong to this list, has to be one of these numbers. But it doesn't say that if the last digit of a number is one of these, then that has to be a square. No, the converse is not true. For example, look at the number 29. Its last digit is 9, but 29 is not a square. In fact, 29 is a prime number. Okay, so the last digit being one of these numbers is not a sufficient condition for a number to be a square, but it's a necessary condition. If something is a square, then its last digit has to belong to this list. And from this observation, we can in fact rule out many numbers because their last digits do not belong to this list. For example, this number, its last digit is 3, which is not here. So it cannot be a square. So that way, it's actually ruled out. 6, however, is present here. So from that, we can't say anything though. We cannot figure out anything about whether this number is or is not a square simply by looking at this list, because 6 is available. 1, again, just like that, is available here, so we can't say anything about this number as well. 8, however, is not available here, so this number cannot possibly be a square. 7 is not available here, so this is also ruled out. Again, we have 8 here, so this is ruled out. And here, the last digit is 1. So again, we can't say anything about that from this. Now you can make this a bit stronger by looking for the last 2 digits of a square by studying these congruences instead. Modulo 100. And when one does so, one obtains these as the possible last 2 digits of any square number, any perfect square. And so, will this new list allow us to, say, rule out some more numbers? Let's see. Here the last 2 digits are 2 and 6. Do we have 2 and 6 here? 24, 25? No. And that's why what the first list failed to do, the second list does. It actually helps us rule out this number as well. This, however, still persists as a doubt. I mean, we can't say anything about whether it's square or not because 61 is available here. But you see, already you have ruled out many things except 2 cases. One of them is this number and the other one is this number. It turns out that this is a perfect square, but this is not. You will, however, when you go through these calculations, you will have to simultaneously see whether you are getting a square or not. So before you get to this, you will get this. And here itself you will have to figure out whether it's square or not. If it is square, then there is no need to go any further. But if it is not, then you continue your calculation. But then if both these lists are failing to say anything about this, what can you then possibly do? Well, you can do something like this. What you do, you just arbitrarily take some integer and see what its square is. If that square is less than this, then you add 1 to that integer and take its square. See if that square is less than this. That way you go nearer and nearer to the number. But if your first chosen number has a square that is greater than this, then you subtract 1 from that number and take the square of that. So that way you come again close to the given number. And in doing so, if some square hits the number itself, then it's a square. Otherwise, if it just jumps the number, for example, going through that same procedure for this number, we see that 345 square is less than n. but the next square actually is also not equal to n, it's greater than n. So n cannot be a square. Okay. Like that, if one does for this number, one will find out that this is not a square. And note that this method does not involve finding square roots of the given number and seeing whether it's an integer. No. You just have to square some numbers and see if it fits this, if it is equal to this. And you will very soon either exceed the given number if you come from below, or if you come from above, you will cross the given number and go to that other side without being equal to the given number. So that happens for this number, and that's why it's not a square. And in fact, in that way also, if one goes for this number, one will find eventually that 69 square is equal to this. So this allows us to really effectively handle the case of figuring out whether these numbers are squares or not. The lists help, but in places where the lists do not help, we can apply this technique. Okay, so that is Fermat's factorization method. Now what? Now there is a generalization of this method. That's what we are going to discuss today. What does the original Fermat's method aim for? Fermat's method primarily means it actually looks for integers x and y such that x square minus y square is equal to n. That's what it is looking for. For example, here 352 square minus 69 square is equal to that n. Instead of looking for this, one can also look for integers x and y such that x square minus y square this time is a multiple of n. This is a special case of this. In this case also, x square minus y square is a multiple of n, but specifically it's that multiple of n which is n itself. Now we are requiring less, so there will be more x and y options, and this is equivalent to the congruence this. That means now we are looking for solutions to this congruence. But say we have found x and y that satisfy this congruence. Then what do we do? Then we calculate either this number or this number. No matter which d we choose, obviously since d is the GCD of something and n, d will divide n. So that way we find a divisor of n as this d. It's a positive divisor because GCD by definition is positive, but do we really get a non-trivial d, that is d greater than 1 and less than n? We don't really know. If we apply this method, who knows for what choice of x and y we will get non-trivial d. Some x and y may actually give us say d equal to 1 or d equal to n, but then it's useless to us. So can we do something about this? In practice, the author says that n is a product of two distinct primes. This thing actually, the author says in practice because you see, factorization in general is a very difficult thing to do. Multiplication is also computationally heavy, if you take two big numbers, then it takes some time to multiply them. No matter what you do, what your calculator does or what your computer does, it takes some time. However, if a number is given, finding its factors is much more difficult than, say, multiplying two or many numbers. So the reverse process is much more difficult, and this difficulty is what cryptographers use for encrypting things, encrypting messages, enciphering messages, making them turning them into something which people cannot understand. Only those who should understand will understand, because they have a decryption method and they know what to do to that encrypted thing, to decrypt it, to turn it back to the original message or original piece of information. And in doing so, there are many things, many ways of doing this. It has been done in ancient times also. We are going to eventually discuss about all these things. And in such methods, the fact that factorization of a given integer is very hard is in fact used. And there one will see in one very famous method, RSA crypto system, there this type of situation occurs. And likely it occurs elsewhere also. I don't really know. But in practice, that's why the author says, in practice, n is a product of two distinct primes. Now, with this additional information, with this form of n, can we now do something extra? I mean, besides doing this, can we do something extra so that we can ensure this, that yes, we will get, if we do that thing, we will get a non-triviality. Let's see. But let us first see what is the consequence of this thing now on our entire thing, on our entire, what will now D be, where P and Q are distinct primes. Say P is greater than Q or less than Q, anything you can take. Alright. Then what can we say about D now that n has this somewhat simple form? It's only a product of two primes, for example 6 or say 40, 2 times 7, like that. Then we know that the possible positive divisors of n are 1, P, Q and PQ, and that PQ is equal to n itself. So obviously D will belong to this set. D has to be one of these four things. We want D to not be 1 and not be n. We want it to be either P or Q. Also, if our x and y are just this, then n, which is PQ, divides x square minus y square, which is x plus y times x minus y. So that means P divides x plus y times x minus y, and Q also divides x plus y times x minus y. Now since P and Q are primes, Euclid's lemma, you recall that property of primes which says that if a prime divides the product of some integers, then it has to divide at least one of them. That is Euclid's lemma. So Euclid's lemma implies that either P divides x minus y or P divides x plus y, and either Q divides x minus y or Q divides x plus y. Fine, so we haven't really done anything new. We are just seeing what is the consequence of n being PQ on this is. Now we are going to see two conditions. So there are in total 4 possibilities that arise from this situation. Either P and Q both divide x minus y, or they both divide x plus y, or P divides x minus y and Q divides x plus y, or P divides x plus y and Q divides x minus y. Now let's see what happens if P and Q both divide x minus y. Then PQ also divides x minus y. Why? Well, that's because P and Q are distinct primes, and so they are relatively prime. They are co-prime to each other. And a corollary to Euclid's lemma then tells us that their product also will divide that same integer, x minus y. So, in this case, our D, if this is the D you are considering, becomes equal to n. Why? Because n divides x minus y, so n itself is the GCD. And that's why this is not what we want. We do not want D to be equal to n. That means we have to avoid this. Similarly, if P and Q both divide x plus y, then n also divides x plus y, but then that other D becomes equal to n. This D becomes equal to n. This is also something we do not want. So, we don't want this, or we also don't want that other condition, that both the primes divide x plus y. And we don't want this. Now, in terms of congruence, what does this mean? See, if this is true, then that means n divides x minus y, or in other words, x is congruent to y modulo n. That's one of the conditions we have to avoid. And if this is true, then n divides x plus y. And in the language of congruence, that means x is congruent to minus y mod n. So, we don't want x to be congruent to plus y or minus y mod n. That means ultimately what are we requiring? Thus, we want integers x and y such that x square is congruent to y square mod n and x is not congruent to plus y or minus y mod n. So this is our additional requirement. Now, will this additional requirement make sure that the d we are going to get is neither 1 nor n? Yes. How? You see, one of those 4 conditions is this: we are avoiding this by requiring x to be not congruent to y mod n. The other of the 4 conditions is this, and we are also avoiding this by requiring x to be not congruent to minus y mod n. Now, that means that so that means that remaining 2 conditions should be true. That means one of them should be true. Either d divides x plus y and q divides x minus y, or d divides x minus y and q divides x plus y. Okay. Now, how does it affect d? Note one more thing, that by avoiding these things, we have already made sure that, we are avoiding both the conditions, that x is congruent to y mod n and x is congruent to minus y mod n. That is equivalent to avoiding those 2 conditions, and that is why no matter which of the 2 d's we use, it is not going to be equal to n, because that's what we were doing. So, by ensuring this, already the d we are going to find is different from n. It cannot be pq, but still, can it be 1? No, it cannot be 1 either. If, I think it will be better if I don't start with if. Suppose this first case is true, that p divides x plus y and q divides x minus y. Yeah, now I write, if d is the GCD of x minus y and n, then x minus y is divisible by q, and n of course already is divisible by q because it is pq, and that's why q divides d. Because q divides x minus y as well as n, so from properties of GCD, q has to divide d. Since d is not equal to n, we must have d equal to q in this case. On the other hand, if you are using this d instead, then this time p divides d, because p divides x plus y and p already divides n. Since d is not equal to n, so we must have d equal to p. So we see that d is either q or p, and similarly if you choose the other condition, then also d is either p or q. You can see why. If p divides x minus y and q divides x plus y, then d is either p or q. Okay, so that's how we make sure that our d is non-trivial. All right. Now let us see one example that will illustrate this method. The number we now have is this 2189, and say by some means we have figured out this x and y. 579 square is congruent to 1881 square mod n. 18 square mod n. How one comes up with these values of x and y, we are coming to that afterwards. But then now what shall we do according to our method? Say we consider that t which uses x minus y. Then we are calculating the GCD of 579 minus 18 and n, and this becomes 561 and n, where n is of course this. And this is where we have to use the Euclidean algorithm to calculate this GCD, which is a systematic procedure. Now, if one goes through the calculations of Euclidean algorithm, of course, this number 561 is less than n. So, ideally we should start by dividing n by 561. If you recall, that's not necessary in fact. You can actually start by dividing 561 by 2189. But then the equation that you are going to get will look like this. 561 is equal to 0 times this plus 561. So 561 itself is the remainder. And then what will you do in the next step? You will divide the divisor by the remainder. So that means in the very next step, you actually again come back to dividing 2189 by 561. That is why it's better to start by dividing the larger one by the smaller one when applying Euclidean algorithm. So if you go through the calculation, the equations are going to look like this. 2189 is equal to 3 times 561 plus 506. So the first remainder is 506. And in the next step, you are going to divide 561 by 506. So clearly you can see that the quotient is going to be 1 and the remainder is the difference. One times 506 plus the difference is 55. Then you divide 506 by 55 and the quotient turns out to be 9 and the remainder is 11. And now you are almost there because 55 is divisible by 11. According to the Euclidean algorithm, the last non-zero remainder is your GCD. So that is why the GCD is 11. And luckily, this GCD is neither 1 nor n. So this is a non-trivial divisor. And in fact, n is 11 times 100, what was the value? 99. I cannot remember all these things. So I have it written down here. If instead of this d, one goes for the other d, that is this one, plus 18 and n, then one finds that the GCD actually is the other factor. Okay, so any one of them will give you success. That way you can find this factorization of the given number. But that question remains unanswered. How does one in fact find this in the first place? Well, straight away if one tries to find this, it will be very difficult. Instead, what the author says, so what he says is that in trying to find multiples of the given n close to some square, these two things were noticed. The task still remains somewhat challenging, but anyway, this was what the process found. 3 times n is equal to minus 6 and (155) square minus 11n, 11 times n was found to be minus 54. So if we translate these things into congruence, into the language of congruence, then we will get this. The first one gives us the congruence 81 square congruent to minus 6, and we are going to write 6 as 2 times 3 mod n. So this is one congruence, and the second one gives us 155 square congruent to so this is 54, no, so 6 times 9, that is 2 times 3 cube modulo n. So you can see that none of these squares is congruent to a square mod n. Okay, so none of these congruences is in fact what we want. It's not of the form x square congruent to y square mod n. But luckily, if we multiply these two congruences, then we get a square on the other side. We have two 2's here, and ultimately we end up getting 4 3's. So the individual congruences do not really give us what we want, but their product gives us what we want. The left hand side is already square, so if we multiply these two congruences, you get 18 times 155 square, and because we are multiplying minus anyway, it becomes plus. And this turns out to be 1,000, well, not 1,000, 12,555. And that is congruent to 18 square. So you already see that we have 18. And it turns out that this large number can be reduced modulo n to minus 579. So that way we get our congruence, using which we can then apply that generalization of Fermat's method to factorize the given number. Still, finding these things may take some time, because you see, you do not immediately get what you want, but you find enough squares. What the author suggests is this: find many xi squares such that modulo n, they are products of powers of small primes. That's the suggestion. Okay, fine. So this is a generalization of Fermat's method to find the factorization of a number that is a product of two distinct primes, 11 and 199. But what if you have more than two primes? You do not know. I mean, when you are starting by considering an integer, you don't really know how many prime factors the integer has. It may not have, it may have more than 2 prime factors. What do we do then? Well, we can apply the exact same method, but the guarantee of having a non-trivial factor as that GCD is then not there. That's because we made sure that D is neither 1 nor PQ only in that case where n is PQ. But if n is, say, p square q cube r to the power 4, where PQ and r are all distinct primes, then that that guarantee is lost. We can, however, apply the method, and if we do, then we may end up empty-handed. The last example of this section gives us such an instance. Even after doing so much, we may actually find that we have not really found anything, no factorization. And this suggestion that find squares which end up being products of powers of small prime modulo n is in fact the basis of a factorization method that was given by the Belgian mathematician Maurice Kraitchik in the 1920s, and that became the basis of modern methods such as quadratic sieve algorithm. I don't know if it is there in this book, but we will see. Towards the end of this book, we actually are going to see many advanced factorization methods. So then we will know. So that means we are now going to see one more example. I think so far Euclidean algorithm is the only thing that is an algorithm in the sense that you apply it to a situation and there is a set procedure, you know exactly what to do and you know that after a finite number of steps you are going to get the GCD. But that's not the case, unfortunately, with many things. You have to struggle by doing ad hoc calculations, by seeing this thing here, that thing there. You then have to mix them up and find it. So the next number is this. One two four nine nine. The beginning, of course, is somewhat like before. Somewhat means it's actually the same thing. Look for squares. The first square that exceeds this. In this case, that is this. And then we proceed by going through those quantities. 112 square minus n, 113 square minus n, okay, and so on. And these things were found for this specific n. These three things were first of all found. Let's see what they are. 112 square minus n turns out to be 45. And 45, of course, is your 3 square times 5. So this is one equation. Then 117 square minus n is this, and this is equal to, it's a product of many primes. Many primes means 4 primes. And then note that we are not getting squares in any of these equations. This is not a square, this is also not a square, but we have one more. 121 square minus n is so here, okay, I haven't written the number itself, or have I? 214, yeah, 2142, and that turns out to be 2 times 9 times 7 times 17. All right. So now if we just simply write these things in terms of congruence, like how we did it back there, what are we going to get? 112 square is congruent to 3 square times 5 modulo n. Then 117 square is congruent to 25717. Mod n. And 121 square is congruent to 2975. 17. 9 of course we will write as 3 square. So now if we multiply these 3 congruences, you see that unlike the previous example, here we needed 3 congruences. So in general we don't really know how many we are going to need, and even after doing everything, whether our D really will be non-trivial, that also we don't know. So if you multiply these congruences, you are going to get 112 plus, times 117 times 121 square is going to be congruent to, we have 2 2's, so we write 2. How many 3's? 4 3's. So we write 3 square, 2 5's, 2 7's and 2 17's. 5, 7, 17 square mod n. Okay, so that way we get gigantic numbers, but we do get x and y, such that x square is congruent to y square mod n. Okay, now how can we reduce this? Because this is very large. 1 5. The left one is 1585584. And the right one is 10710 modulo n. But it's we are unlucky here. The reason is that unfortunately 1585584 itself is congruent to this number. So that means x is congruent to y mod n, and that is why we won't really get a non-trivial D, no matter which D we use. So even after going through so much trouble, we did not get anything in return. Unfazed by this failure, if we still continue, we will get these other equations. Other equations means other congruences, just like we got these congruences, one can also get these congruences instead. 113 square is congruent to 2 times 5 times 3 cube mod n. Okay, so this is another congruence like that. And there is another one, 127 square is congruent to 2 times 3 times 5 times 11 square mod n. Now here you can see that again we now have a situation like that. Here only with 2 congruences, if we multiply them, we are going to get a square, because there are 2 2's, 4 3's, 2 5's, and already here we have 2 11's. So using these 2 congruences, we are going to get 2 times 3 square times 5 times 11 square modulo n. And this turned out to be, the first one becomes 1852 and the second one is 990. And this time, unlike that one, 1852 is not congruent to 900, it's neither congruent to 990 nor congruent to its negative. So yes, now we have finally got a congruence with that extra condition. So the GCD that we are going to get will be in fact a non-trivial divisor. So if one uses the first GCD, which involves difference, then one gets 431 as the GCD value. And 431 obviously is not equal to 1, and it's also not equal to the given n, and that's why it's a non-trivial divisor. And in fact, n turns out to be equal to 29 times 431. So that way, by playing with such congruences, one can in fact factorize an integer if one is lucky. You see, these are not some things which you will in fact find out. You may never find out these things, even if they are there, out there somewhere. It depends on luck. It also depends on experience with numbers, and it also depends on what machine you are using for finding these things. You of course cannot hope to find these things by doing calculation on paper on your own. You have to use some kind of software, something. Okay, so factorization is itself a very difficult and large area. People are still finding new things here, and it's an active area. If we put the theoretical importance of the thing aside, if we don't even consider that, from a practical point of view also factorization is important, because based on the perceived difficulty of factoring an arbitrary and large integer, many encryption methods have already been devised and are in use. So if someone comes up with a new factorization method that significantly improves the situation, say one can now factorize some integer which previously was not able to be factorized, either because no one knew how to do it or because it was prohibitively time consuming, then those encryption methods which are based on factorization, they will be put to risk, and then mathematicians would have to devise stronger encryption methods. So it's always like a war between two sides. One side is trying to find stronger methods for encrypting messages, encrypting things which should be hidden. The other side is trying to break it. That's why also factorization is important. So this is where this section ends, and after this we have usual exercises that we will see next. So that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.